All right, thank you. Welcome back to calculus. So we're going to look at finding the area between two curves. Now, before, when we do any type of integration or Riemann sum, what we were doing was we were finding the area between two curves. That's just what we were doing. Or finding the area between the curve and the x-axis. So what we are looking at now is what happens when we start looking at the area between two curved pieces. Well, we're still essentially doing the same thing. And I've just gone to Desmos here, and I've created the image and grabbed a screenshot and just embedded them here in OneNote for us. And all I'm going to do is I'm going to say, well, let's look at these. I got the red curve right here, which is just your plain ordinary happy Mr. Parabola here. And you got your sad Mr. Parabola up here, the blue one that's got the frowny face looking down. And I have these two functions that are describing these two events. Now, if I were just to do the integration of just, and when we look at these two places, we can kind of find these values. And I could have made these numbers easier to work with, but I'll come back to that here. We're going to go from right here, which looks to be about 1 3/4 right here, negative 1 3/4. But we're wanting to identify that intersection point there and that intersection point right there. But we'll come back to that here. So we'll just, for right now, I'm just going to call this A. I'm going to call that B. So A and B, and we'll come back and find those numbers here in a second. Now, what I'm doing here is let's just do the integration from A to B of x squared dx. Now, what is that? Now, that's the parabola that's opening upward. So what I'm doing there is if I draw these lines down like this, what I'm finding is I'm finding this area right here between that red curve and the x-axis. Now, that wasn't drawn very well over here on the right, so I do apologize, but oh well. Now, so that's what that is, right? So let's get rid of that and that. What if we want to do the integration from A to B of negative x squared plus 5 dx? What is that? Well, that's still starting right here. It's still going to right there. But now what we're doing is we're finding all this, right? Finding all that space right there. Well, that's all that area, right? So remember the first one we did, we talked about that was this area down here. So what I want to do here is take this bigger piece, the one that is on top, and notice it changes too. And we can work a couple different examples with this one set of equations here. Really what I end up doing with this now is I'm going to do the bigger one, the integration from A to B of negative x squared plus 5. And I'm going to subtract off the smaller one, or the underneath one, of just x squared. And I can put that all in the same integration sign, or I could have left them as two separate integrations. Either way. So now I'm just doing the top one minus the bottom one, the one that's larger, the one that has the larger y values on that interval, and subtract off the one with the smaller y values on that interval. Okay? And we can look at multiple intervals on this region here, and see what's going on with these pieces here. Okay, so there's that. So what we'd want to do then is we'd want to take x squared and set it equal to negative x squared plus 5, right? And find the intersection points of A and B. So that means we got 2x squared equals 5. I could actually move the 5 over to the other side and use the quadratic formula on this one. But since I don't have a middle term, I can just continue solving it like this. So I end up with x squared equals 5 halves. So that means that x is equal to plus or minus the square root of 5 halves. Now I have to put that plus or minus in there because I'm starting off with a square, which means there's two ways I could get 5 halves. I could do whatever decimal this is times itself, or the negative version of this decimal times the negative version of this decimal, which would also, in both instances, give me that positive value. Now, this works out to be some decimal of some sort, but when we're doing this integration, I would strongly encourage you to go back and stick with the exact value of what we're working with. Now, this works out to be 1.58-ish. Okay, there's actually a 1 on the end of that right there. And it just keeps going on and on forever. Now, this is an approximate value. So if you were to stick these approximate values in right here, you're not going to get the exact value. So what I would say do is just use the exact value, okay? So right here, I would do negative root of 5/2 and positive root of 5/2. It's really not going to make a huge difference when you start evaluating this. So we do this integration, we're still doing negative 5/2, square root of negative 5/2 to positive square root of 5/2. And I'm just going to simplify this a little bit, so I end up with negative 2x squared plus 5 dx. So then I'm going to integrate that, which gives me negative x to the third over 3, I forgot my 2, plus 5, and evaluated from negative 5 over 2, square root of negative 5 over 2, to positive square root of 5 over 2. So we just plug those in, so we get negative 2, and you get square root of 5 over 2 cubed over 3 plus 5. Oh, I forgot my x, didn't I? X right there. Yeah, there we go. And then square root of 5 over 3. Okay. And then minus negative 2, let's see here, square root of 5 over 3 cubed over 3 plus 5 times negative root 5 over 3. Okay, there we go. Now at this point, I would get my calculator and quite literally just type this in exactly as I see it, and I would get some type, and I put an equal sign there, which is actually wrong. It's not going to be equal at this point. I'd go use my calculator and get the exact, as close to that value as I possibly can, and then at that point it would be an approximate value of some sort. So that is what we would end up with, and that the actual value here is less important to me, and of course in this case you'd be units squared, right? As much as the actual process is that we're going through that, you can do these calculations on your own, okay? Now what else can we do with all this? Well, one of the things we can also do is we can do a completely different scenario with these values here, right? So let's just kind of look at that for a second and talk about what else we could do with that, okay? So how else can we deal with this one? So I'm just going to recreate, instead of erasing all that, I'm just going to create a whole new drawing here. So I'm going to grab this and I'm going to go, what if we're going from here to say here? No, that's not right there, right here, where the 2 is, okay? So we want the overall interval. We want to do the integration of that entire region there from 0 to 2, okay, of all that stuff dx, right? Now the problem we run into in that particular instance is what's happening right here. Now we've already found this value right here is square root of 5 over 2, so we don't have to do that refiguring, but again we just set the equations equal to each other. Now the problem why I'm bringing that up is because right here it switches. So what we'd be doing is from 0 to that spot, the blue curve is on top. It has they have larger y values. At that spot right there, the red one turns into the one having the larger values. So we'd have to split this integration up from 0 to the root of 5 over 2, and we would do negative x squared plus 5 minus x squared dx, all right, and that'd be the entire first part of that. And then we need to add to that the integration from square root of 5 over 2 to 2, and they switch. X squared is now larger, and then we have to do minus negative x squared plus 5. And that changes some of the nuances of those values that we'd get out. Not very much, but it is a big important flip there. And I hope you see how that switches. All right, so just to kind of point this out again, this little section right here, that is from here to there. So that's all this area right here, right? Okay, and then you're like, well, what's the rest of that? So this This next one here is this right here. This piece is this region right here. Okay, some of you may have been thinking that was below there, and that's one of the reasons why I wanted to make sure I shaded that in, is because that's a big important aspect of what we're dealing with there. Okay, is making sure that you can identify those pieces. All right. So I hope this was helpful. If you need additional explanations or additional examples on how to work out area between two curves, please reach out. And remember, ultimately the idea, the thing that you want to do is identify intersection points and identify which curve is on top. And understand that you might have to switch at some point on the interval that you're being asked to identify. So if we were looking for find the area, what we did here is find the area on the closed interval from 0 to 2, and unclosed is another way of saying the inclusive interval. We're including the endpoints. Find the area between 0 and 2 of function f and function g, where this was f and this was g. And what we did here was we did f minus g, and what we did here was g minus f. Okay, and we switched that where the two functions were equal to each other. And of course, f was equal to g at x equal to root 5 over 2. Okay, cool. I hope so, at least. Let me know if you need additional examples or you have additional questions about this one. Take care.